Now we should be live.
Okay, great.
So let's see. Yeah, you wanna
Yeah,
try and give a summary
yeah,
of this?
yeah, yeah. So yeah, I'll just give kind of the background of kind of yeah the relevant information for where we're at. So we're looking at two's complements, where a two's complement is like another way of representing a number or an integer, specifically in binary. Um, so the definition is like well, I guess firstly we need to have like some bit length, meaning like some number of bits that we're going to use to represent numbers. Each bit can have either a 1 or a 0. Um, so like for some fixed bit length n, the 2's complement of a number a is going to be 2 to the n minus a. And that's the definition of a 2's complement. 2 to the n minus a, written in binary. And these are going to be useful, they can be convenient for doing arithmetic more easily, and also um, they can provide a convenient way of representing negative integers. Um, so firstly, um, last time we saw kind of a proof of a general procedure for finding a two's complement. Um, so if we have an integer and we want to find its two's complement, first we can write it in binary, and then we flip the bits, meaning switch the ones to zeros and the zeros to ones. Oh yeah, and this is on page 85. Yeah, so write it in binary, flip the bits, turn all the ones to zeros and all the zeros to ones, and then add one, still working in binary notation. And the result of that is going to be the two's complement. So that's kind of a nice shortcut. If you do that, you'll get the two's complement. Um, and yeah, so looking at page 86, actually we can go to 87. Or sorry, 80. Actually, let's do the bottom of 86. So like just to simplify, we're gonna suppose that we're working with 8 bits. So we're interested in all the numbers. We're gonna be using 8 bits to represent them. Um, and there's a limit to how many integers you can represent with just 8 bits, because um like numbers like 1572, like that's going to require more than 8 bits to represent in binary. So you can't represent anything with 8 bits, like absolutely everything with 8 bits. But yeah, we'll work with 8 bits, and then so that by definition the 8-bit two's complement is going to be 2 to the eighth power minus a, if a is like the number that is like a if you have a number a and you want to find the 8 bits two's complement, that's 2 to the eighth power minus a. So, um, so we're gonna do like a so we're gonna use two's complements to come up with a way of representing negative integers. So what we're gonna do is we this is a there's a way of representing with 8 bits all of the integers from negative 128 to positive 127, and it works like in the blue box there. Um, for the non-negative integers, meaning 0 and the positive ones, just represent them as usual in binary notation, using 8 bits. So that might mean that you have like some extra zeros at the beginning to make the numbers fill up 8 bits. Like for example, the number 1, you'd have 7 zeros and then a 1. Um, and then for the negative, and that's gonna cover that's gonna cover half of the possibilities with 8 bits. Um, or yeah, it's gonna cover half of them. And then for the other half, we're gonna have the numbers from -1 to negative 128, and we're gonna use the remaining possible 8-bit representations to represent those. And at the top of the next page, there's a chart where you can see that the remaining 8-bit representations are the ones that have a leading 1. They have like a 1 as their leftmost digit. And all of those are going to be the ones representing negative numbers. And each negative number is going to be represented as the two's complement of its absolute value, where the absolute value of the negative number is like the positive version of it. So the absolute value of -1 is 1, the absolute value of -2 is 2, and so on. So, so yeah, to find the binary in this way of representing integers, if we have a non-negative integer, we can just represent it as usual in binary notation using 8 bits. If we have a negative number, we find the 2's complement of its absolute value, and then that's going to be its binary representation. Yeah, and then at the bottom of the page, there's a procedure for adding integers from -127 to 128. And this procedure works only if the integers are in that range, and also if their sum is in that range. So like, yeah, the sum of the integers has to be in that range as well. So the procedure is like, firstly, you write each of the integers you're adding using binary notation in the way that we're doing, where you represent non-negative ones in the usual way, and then negative integers as the 2's complement of their absolute value. So first you write those 8-bit binary representations of them. Then you do kind of ordinary binary addition. And then you get rid of any leading one that occurs like in the 2 to the 8th position, meaning like if you have 8 bits, the rightmost bit is going to be 2 to the 0, then you'll have 2 to the 1, and it'll go all the way up to the 2 to the 7th place. That's going to be the leftmost one if you have 8 bits. If you end up with 9 bits, you have something to the left of the 2 to the 7th place, that'll be the 2 to the 8th place. So like if you get if you do addition and you get something with 8 bits, then you're good to go. But or you're almost there. But if you have like a 1 in like a 9th spot to the left, then you just get rid of that 1. And we're gonna see soon like why it's okay to do that. Why that still gives you the right sum. Yeah. So once you've done that, you've got the sum in binary form, and then you can convert it to decimal form. And also, by the way, like, so if you have a leading 0, all the ones with leading zeros for their leftmost digit, those are going to be non-negative integers. So you can just convert those to decimal as usual. But if you have, like if you have a leading 1, the ones with leading 1s are going to be, those will be negative integers. So for those ones, I think you would, yeah, to figure out what those would be in binary, in integer like a decimal notation, then you would have to let's see. So oh yeah, so you would have to like I think you have to take the 2's complement again. Or no.
I remember we went over this. I'm trying to remember how to convert it from negative.
Yeah, I think it's like you take the, so you know that the representation you have is the 2's complement of the absolute value. So I guess if you take, oh yeah, so like there's this it was also shown last time that like the 2's complement of the 2's complement is the number itself. So if we have this something with a leading 1, then we know it represents a negative integer, and we know that it's the 2's complement of the absolute value of that negative integer. So I think if we just like we take the 2's complement again, then we're going to get back to that absolute value, and then we write that absolute value in decimal notation and put a negative in front of it.
Huh. Yeah, I do remember that being somewhere earlier.
Yeah. Yeah. Oh yeah, that was at the top of page 86.
Right. To get A, you get the 2's complement of the 2's complement. The 2's complement would be the A, I guess, of the outer 2's complement formula.
Yeah.
To get the inner A.
Yeah.
Okay.
Yeah, exactly. So like if we have Yeah, if we have something that we know it's a two's complement and we want to find out what it's the two's complement of, then we take the two's complement again, and then we get that the original number. In this case, we get the absolute value um, of the original number if we're working with if we know we have the two's complement of the absolute value, and then we would just put a negative.
So just real quick, maybe we should like go over what we learned. So one was how to find the two's complement.
Yeah, yeah. So how to find the two's complement, and then I guess we also saw like going both ways. Like if you have something in decimal notation, you can find the two's complement in binary. And if you have the two's complement in binary, you can go the reverse direction and find what that number would be in decimal notation. Um, and then we also saw like this scheme for representing numbers from negative 127 to, or sorry, negative 128 to positive 127 in binary using two's complements of the absolute values for the negative numbers.
Oh,
And then we saw a procedure like for adding.
so wait, what did you say after? So we found the two's complement, and then we also learned.
Yeah, yeah. So we learned how to find two's complements, and then we learned like this way of this way of representing all the numbers, all the integers from negative 128 to positive 127 using 8 bits. Um,
Uh,
and that method was for the numbers from 0 to 127, we just represent them in binary as usual. Um, all of those are going it happens will have a leading 0. They'll have a 0 in the leftmost spot if they have 8 bits. Um, and then the negative integers from negative 1 to negative 127, each of those is going to be represented as the two's complement of its absolute value. So, for example, like um, the two's comp or negative 1 would be represented as the two's complement of positive 1, meaning 2 to the 8th minus 1. Um, and it happens that all of those two's complements of the absolute values, those would all end up having a leading 1. So a number can be recognized as negative if it has a leading 1.
okay. And then I guess what after that did we learn how to subtract in binary?
Yeah, pretty much. It's because yeah, I guess it's like you can consider it to be either addition or subtraction because like if you say like 1 minus 2, that's the same as 1 plus negative 2.
Right.
Um, yeah. So yeah, this does give us a way of subtracting in binary. But I guess they consider it in terms of addition because then that makes it easier to calculate because we already know how to add in binary.
Right.
Um, yeah, so they came up with like using this scheme for representing numbers from negative 128 to 127. There's this procedure for adding numbers in that range as long as the sum is also in that range.
Hmm.
Um,
I guess you could
so
use
you
those
first,
adder circuits.
yeah, yeah, I guess it could have been done with those too. Yeah, but
Hmm.
here they're having us kind of do it like I guess manually, like yeah, like going through all the arithmetic.
Like you don't need like a separate subtraction circuit in order to subtract. Like if you were to make a calculator, um, yeah, I guess the adder circuit would be able to handle addition and subtraction now, since we can represent negative numbers.
Yeah, yeah, exactly. Yeah, although we might need to like do things to the adder circuit, like um, because like if we have a negative, or let's see, if we, I guess we need to like tell the adder circuit to like get rid of like the leading one if there's like an
Right.
overflow. So we might need to do some additional things to it,
Yeah.
but it would mostly be the same.
Hmm.
Yeah, but yeah, let's like so the procedure like we write the binary representations of both of the integers. The integer is non-negative, the binary representation is just the usual binary representation. If the integer is negative, the binary representation is the two's complement of its absolute value. And then we add them like as usual for binary numbers. or numbers written in binary. Um, then if there happens to be a one, like in a ninth spot to the left, then that's an overflow, and we get rid of it. Um, and then put the results back into decimal form. If the result begins with a zero, then we know it's non-negative. If the result begins with a one on the left hand, like the far left side, if it has a leading one, then we know it's negative. And since it's negative, to find what it is in decimal, we'd need to take the two's complement of it, and then that gives us the absolute value of the negative number. And then we just put a negative in front of that.
Yeah. So we can also obtain
Yeah,
the absolute value of negative binary numbers.
yeah. I guess it's kind of like I think we're kind of like starting out with the numbers being in decimal and then taking the absolute value, and then converting to binary.
And then didn't we also learn that the absolute value of the negative binary number is the two's complement of the negative number? Like, I guess if you wanted to represent it
Oh
in
yeah.
decimal, you would need to get the two's complement of the negative number.
Oh yeah, yeah, that's true. Yeah, because like as the negative number by definition, it's represented as the two's complement of its absolute value. So if you take the two's complement again, then you get back to the absolute value. So the two's complement of the negative number is its absolute value.
So, and that's in order to represent it in the decimal form. So, like, if you have a negative binary number, do you first n- need to write that in a form that would fit into the two's complement formula?
Uh, well, I guess you need to have it as long as it's 8 bits. You can kind of define the two's complement. You would flip the bits and add one.
Oh, you're right. Okay, okay.
Yeah, so we have like the general procedure for finding the two's complement of any number in binary.
I see.
Yeah. Yeah, and then like what we started last time after this was like um kind of pretty much a proof of the that what's in that blue box, like because it's not really obvious that like this procedure would work in the sense that like this procedure really would give us the sum in every case. Like it's not like obvious that like it's just okay to just get rid of that leading one sometimes if there's an overflow. Um, so like the proof went through different cases and showed that like in each possible scenario, like maybe both of the numbers are non-negative, they're both negative, that kind of thing. Like in each of those scenarios, this procedure really does give us the sum. And we did the first two cases, and then we're on the third on page 89.
Oh, yeah, let me see. Gives us the sum. So, what were these cases?
Oh
Both.
yeah, so like these
Yeah, what was the point of this proof here?
oh yeah, so the proof it's kind of to prove what was in the blue box. So like it's kind of like they want to show that no matter which A and B you pick, uh their sum can in fact be calculated correctly by following that procedure.
Okay, yeah, yeah. As long as the sum is within the range, right?
Yeah. Oh yeah, exactly. Yeah, so there is that restriction.
Hmm. I wonder if there's a way. Oh, there is a way to ensure that the sum is within the range, right? There's like a some limitation you can put on the inputs that makes this the case. I guess that's a part of the proof as well.
Yeah. Yeah, and I guess in the proof they might assume that in each case the sum is in the range. They kind of just assume that the numbers you picked are ones that keep the sum in that range.
So imagine if you're making a calculator, like you would need the inputs to be restricted in such a way that the sum is always within the range. It can't be
Yeah.
Yeah, yeah. That you don't know ahead of time that the sum will be within the range, I don't think.
Well, I guess um I mean, I guess like the one you do like for any given pair of integers, you can just add them in decimal and check if the sum is in the range.
Right, but if you're like building something, you would need to restrict the inputs to ensure that no input could be outside of what your system can handle, I guess.
Yeah.
And I think the proofs here do somehow illuminate um what the inputs restrictions are, unless maybe I'm wrong about that. Let's see.
Yeah, they might. I mean, I guess a calculator could still um like it could just quickly it could maybe there's a better way to do it, but the calculator could just kind of calculate the sum in binary, and then if the sum is outside of the range, then it'll just say error. And then if the sum is in the range, then it goes to the next step.
Hmm. True. Let's see.
Yeah.
Okay, so that's the steps for adding the numbers. And you're saying that this proof, what does it explain?
It shows that like for any a and b that are in the range and whose sum is in the range, this procedure, like those series of bullet points, really does give you the sum
Okay.
in every like it'll always give you the sum as long as those restrictions are met, so that the numbers are in the range and the sum is in the range. Yeah, and then they consider like four different cases depending on like whether the numbers are non-negative and like how their absolute values compare to each other to kind of exhaust like to cover all the possible cases.
Yeah. I guess what interests me is how it's truncating the leading one still leads you with the correct answer in those cases where you need to do that.
Yeah. Yeah, I was curious about that too. I think they explained that in case 3.
Okay, let's see. So, well, case one is both integers are non-negative, which you just add them, right? And you should be okay. Second one is a non-negative. Um, A is non-negative and negative B is negative, and the absolute value of A is less than the absolute value of B, so it's more negative.
Yeah, it's like more negative than A is positive, or than A is non-negative.
Okay.
Yeah. So that one we did, but maybe it's worth looking at again because it was a more complicated one.
Right. So we're finding the 2's complement of B here, and we're adding it to A. That's what it's like, A plus negative B, which is what we're going
Yeah.
to do with the process, the procedure.
Yeah. Yeah, because we're doing, yeah, exactly. We're doing A plus negative B, and negative B by definition, that's the two's complement of positive B.
But now, why did they transform it into finding the 2's complement of B minus A?
Uh, I guess, yeah, they must, probably in the later steps it'll become clear why they did that, but I guess it just like they kind of just rearranged the they rearranged the expression like 8 2 to the eighth like this is A plus 2 to the eighth minus B. So they just move the 2 to the eighth to the left, and then so then they have A plus A minus B. A minus B is the same as minus B minus A, because like if you have a minus, like if you're subtracting like some sum or difference, it's the same as like applying the negative to each part of that sum or difference. So like subtracting b minus a is the same as subtracting b and adding a, which is what we have on the left side.
I guess they're trying to get to this left side formula here because that's exactly how the binary subtraction looks.
Yeah, yeah, exactly. Yeah, because they want to show that like it's okay to like if you take the two's complement of the absolute value of the negative number, and add that to A, you're still gonna get um the actual sum.
Oh, I know the formula starts off with a plus the two's complement of b. And we've already accepted that the two's complement of b is equal to negative b. But I guess they're just reminding us that there is like this algebraic way to reach that conclusion.
Yeah, well, I guess they're saying, yeah, like by definition, in this procedure, we're representing negative b as the two's complement of positive b. And they're checking like because the procedure says that like you represent a and b, um, you represent a in binary as usual, and since you have negative b, it's a negative number, you represent that as the two's complement of its absolute value. So this is how the procedure tells us to calculate this sum. And so they're going to check if the procedure actually gives us the sum. So to check that, they need to like follow the procedure and say like a instead of a plus negative b, a plus the two's complement of b.
Right. And then here's kind of interesting. So it says we must be careful to check that the two's complement of b minus a is between um, 2 to the 7th and 2 to the 8th.
Yeah. Yeah, so the reason for that is that the numbers from 2 to the 7 between 2 to the 7 and 2 to the 8th, those are the ones that have a leading one. Those are the ones that will be represented as negative, or
Oh,
those are the ones that represent negative numbers.
okay.
Yeah. So we have yeah, 2 to the 8th minus b minus a, that is the two's complement of b minus a. And b minus a, by the way, because we know that the absolute value of b is greater than the absolute value of a, um, that means that, and we know b is positive since negative b is negative. So pretty much like b is greater than a, so b minus a is positive. Um, so that means that negative b minus a is negative.
Right. And then their proof
Yeah,
is 2 to the 7th is equal to 2 to the 8th minus 2 to the 7th. Um,
yeah. And then like to show that, I guess we could kind of just calculate them like what 2 to the 8th is and what 2 to the 7th is, but we could also factor it. Like take out what the two parts of the difference have in common. Like 2 to the 8th is 2 to the 7th times 2. 2 to the 7th is 2 to the 7th times 1. So we could pull out the 2 to the 7th and say like 2 to the 8th minus 2 to the 7th equals 2 to the 7th times parentheses 2 minus 1.
right.
And then 2 minus 1 is 1, so it's 2 to the 7th times 1. So then 2 to the 8th minus 2 to the 7th does equal 2 to the 7th.
And then they need to prove that 2 to the 8th minus b minus a is greater than 2 to the 7th.
Yeah, or that it's less than 2. Oh, wait, that's greater than or equal to. Yeah, yeah. Um, yeah, so they know, so they say that 2 to the 8th minus 2 to the 7th is less than or equal to 2 to the 8th minus b minus a. And that's because, um, well, we know that b is greater than a. Um, a and b, they're both numbers from 0 to 127, because b is the absolute value of some negative number from 0 to uh, negative 1 to negative 128. So I guess b and a are actually from 0 to 128. But um, so we have like some number from 0 to 128 minus a smaller number from 0 to 128. Um, and
Okay. So
128.
is 2 to the 7th, right? So
Yeah.
the biggest that number can be, b minus a, the biggest it can be is 2 to the seventh minus 0, I suppose.
Yeah. Yeah, exactly. Yeah, which means that
It's
this number
going to be greater than or equal to 2 to the eighth minus 2 to the seventh.
yeah. Yeah, because 2 to the 7th it's either equal to b minus a, or 2 to the 7th would be
Right.
bigger than b minus a. So like you're subtracting something that's the same or possibly bigger, 2 to the 7th.
Hmm.
So that means that like 2 to the 8th minus 2 to the 7th is less than or equal to 2 to the 8th minus b minus a.
Hmm. And then that
Yeah.
it's going to be less than 2 to the eighth because of the subtraction.
Yeah, yeah, because we know that b is greater than a, so we're having like some bigger number minus a smaller one, and that can't be zero because you're subtracting one number from a different number, like a bigger positive number minus a smaller positive number, so it's 2 to the 8th minus something positive, which will be less than 2 to the 8th.
And why isn't it a problem that our sum, it's not a problem if our sum equals 2 to the seventh?
Uh, if the sum, oh yeah, because 2 to the 7th, that would be like a leading one with seven zeros after it, and that's like within the range that can represent negative numbers.
Okay, so out of bounds would be 2 to the eighth, right?
Yeah, because then that would be like an overflow. That would have 9 bits, like a leading one with 8 zeros after it.
I see.
And also, if you're less than 2 to the 7th, then you end up with a leading zero.
If you're less than 2 to the seventh, if you're less than 2 to the seventh, you end up with a leading zero.
Yeah, because if you have 8 bits, the leftmost spot is the 2 to the 7th place. And if you're less than 2 to the 7th, there's going to be a zero in the 2 to the 7th place.
I see, I see. Has to be negative. Interesting.
Yeah.
So the since it's a negative, the answer has to be quite big to represent it correctly in binary. Like I guess you could say like the, I don't know, the absolute value or just the decimal representation of our sum has to be quite large, or it has to be within 2 to the seventh to 2 to the eighth.
Yeah. Yeah, it would have to be. Yeah, well, the decimal representation of the two's complement,
Right. Well,
of the
like,
absolute value, yeah. But then I guess to find what the actual sum would be in decimal, I guess we have to take the two's complement again and then put a negative in front of it.
right. I wonder what you call that number, like before you get the two's complement to represent it properly, like the just raw um number, if you weren't thinking of the leftmost bit as the negative or positive bit.
Yeah. Yeah, I guess yeah, I wonder. I guess they could call it the two's complement or the decimal representation of the of the binary the decimal representation of the binary, or no, the decimal representation of the two's complement of the absolute value of the decimal number. That would be a pretty long way of putting it, though.
the So it's the two's complement of the absolute value of the decimal number.
Yeah, because the decimal number was like a negative, so it's represented as the two's complement of its absolute value. And in this case, um, so like if you kind of have the representation of the negative number, and then you just put that in binary, then you'd have, or you put that in decimal, that decimal number would be the decimal version of the two's complement of the absolute value of the negative number.
Really? So let's do an example. Like let's say negative 2 using, I guess, 8 bits would
Yeah.
be,
Well,
let's see, 2, and then you flip all the bits and then you add 1. So you end up with a bunch of ones and a 0 at the end, right?
let's see. So So two is going to be like you'll have six zeros, then you'll have a one in the twos place, and then you'll have a zero. Then yeah, exactly. Yeah, you would have like six ones, then a zero, then a one. Um,
So,
then you add one.
so this is
Yeah.
the two's complement of the absolute value of -2, which is 2. All right, so this is the two's complement of 2.
Yeah, exactly. Yeah. So yeah, that's how negative two would be represented in this system.
Hmm.
And then we could calculate like what that would be in decimal. I guess that would uh um
I am
it would be like
curious
probably like 126 or something, or maybe one, or
because
maybe
8 bits is, yeah, 128. Wait, no. 8 bits is 2 to the 8 minus 1, right?
yeah. Yeah, like 2 to the eighth minus 1 would be the maximum thing that could be represented with 8 bits.
And we have, so 2 to the 8 minus 2 here. And then 2 to the 8 is that 256?
Uh, it's I think so. Let me double check it. 1632. Yeah, 256. So that minus 2. So oh yeah, 254 actually. Oh yeah.
Hmm.
Oh yeah, you're right. I was thinking in terms of 128, but yeah.
Let's see. Okay.
Yeah, so negative 2 like doesn't actually equal 254, but it's kind of in a way represented as 254 'cause it ends up being convenient in binary notation.
And then you think, I guess, -3 would end up being 253?
Yeah.
I I doubt the chapter is going to get us a whole lot of familiarity with this number, but in like how addition and correlates with this number. But interesting. I see right here it sort of got some importance. That number has to fit within the bounds here. It has to be between 2 to the 7th and 2 to the 8th in this case. Because it has a leading 1, which helps us represent negatives. But
Yeah.
yeah, interesting, interesting. There's a lot that I could think about with this number, but I don't know. I guess we're just gonna leave that up to us to think about in our free time. I don't think they're really gonna talk about
Yeah.
it.
Yeah. Yeah, I guess yeah, it kind of ends up being a convenient way, like because you want to like if you want to represent both positives and negatives with 8 bits, then like you kind of just like you take you give half of them to the positives, and then half of them to the negatives within some range, and then like so that means you're kind of giving negatives binary representations that correspond to like bigger positive numbers. Um, yeah, but I guess
Right.
there isn't Yeah, but there isn't anything I guess, special about the number 254, but it's kind of like if you follow the procedure, then it works to give you the sum.
Right. And then like the for 7 bits, 2 to the 7, um well, yeah, 2 to the 7 equals, was it 128, right?
Yeah, yeah,
So 127 is the highest you can represent with 7 bits.
yeah. Or with oh yeah, it's the high. Yeah, it is. Yeah,
So to represent negative numbers, you would need the numbers between like 128 and 255.
Yeah.
inclusive. Yeah.
Yeah. Yeah, exactly. And that's why you have like a leading zero for the ones from 0 to 127 because those could be represented with 7 bits, so you actually don't really need the eighth one on the left.
Hmm. So, okay, when we're trying to get a negative number, well, in the case where we have A as positive and B as negative, um, the two's complement of B plus A would need to land between 128 and 255.
Yeah. Yeah, the two's complement of the absolute value for a negative number would be in that range. Because like the negative numbers, those are the ones, or for in terms of for these purposes, they're the ones from -1 to -128. So the two's complement of those, that's going to be 256 minus something from 0 to 128. So that's gonna end up being from 128 to 250, or from I guess yeah from 128 to 255 if you subtract something from one to sorry from one, not from 0 but from 1 to 128. If you subtract it from 256, you get something from 128 to
True.
255.
Which is what they're saying here, except they're just using the powers rather than the numbers.
Yeah.
Okay. Let's see.
Yeah. Yeah, so they're kind of showing like algebraically using the definition of two's complement. Yeah. Yeah, and then we did that example, but haven't done case 3 yet.
Okay, let's see. So A is non-negative and B is negative. Well, it says and negative B is negative, and the absolute power of B is less than or equal to the absolute power of A. So when I say
Yeah, or the absolute value.
negative B is negative, wouldn't that mean that B is positive?
Yeah, it would. And I think they're doing that, trying to make it easier, because like they could have just said like we're taking the sum of A and B, and then they could say like A is non-negative and B is negative, but then that could be confusing. That could be confusing because like then yeah, I can kind of forget like whether B is positive or negative, so they kind of just make all of the variables represent positive numbers, and then just write negative B, for the negative thing you're adding.
Okay, so they mean okay, okay.
Yeah,
So
but yeah,
negative
exactly.
B,
B is positive.
gotcha. Negative B is negative is redundant. Or maybe it's
Yeah,
not.
well,
Negative
yeah, not
B
necessarily.
just means the negation of B, not necessarily that it's negative, right?
Yeah, yeah, the opposite of it. Because like, what if B was itself negative? Then negative B would
Right.
be positive. Yeah,
Okay. Now absolute power of B is less than A. So it's going to be a positive number.
yeah, yeah, exactly. Yeah,
Or zero.
um, yeah, the absolute value of B, what yeah would be a positive number, and that's less than or equal to the absolute value of A. So that means the absolute value of A must also be positive. And then they say like so like by definition, if you're adding A and negative B, and that's going to be well, A is just going to be the binary representation of A. B negative B will be represented as the two's complement of its absolute value, so 2 to the eighth minus B. And then they kind of just rearranged. They rewrote that as 2 to the eighth plus A minus B, and they have a series of inequalities. 2 to the eighth is less than or equal to 2 to the eighth plus A minus B. So A minus B, the absolute value of A is greater than or equal to the absolute value of B. So you're taking like the absolute values are equal to the A and B respectively. So you're taking like a bigger thing and you're taking like a bigger positive number and subtracting a smaller positive number. So that's going to give you a positive number. So 2 to the eighth plus a minus b is 2 to the eighth plus some positive number, which would be bigger than just plain 2 to the eighth. Or I guess, oh yeah, I guess or equal, because a could be equal to b. Absolute value of b is less than or equal to the absolute value of a. So it's 2 to the eighth plus a positive number, or 0, that's greater than or equal to 2 to the eighth. And then 2 to the eighth plus a minus b is less than 2 to the eighth plus 2 to the seventh. Um,
Because yeah, well, like a is less than 128 by our restriction.
yeah. Oh yeah, exactly. Yeah. And so that means that so the binary representation of a plus 2 to the eighth minus b. So they showed that 2 to the eighth plus a minus b, that's equal, so 2 to the eighth plus a minus b equals how we're representing the sum. Show that 2 to the eighth plus a minus b is between 2 to the eighth, or it's greater than or equal to 2 to, no, it's less, it's, uh, oh yeah, they showed that um it's greater than or equal to 2 to the eighth, but it's less than 2 to the eighth plus 2 to the seventh. Um, um, so 2 to the eighth plus 2 to the seventh, that's mm, I guess that, well, that's, oh, well, 2 to the eighth plus 2 to the seventh, that's gonna be less than 2 to the ninth, I think. Or no, is it? Let's see.
Yeah, I think it.
256 plus 128. Oh yeah, yeah, 2 to the ninth is 512, so 2 to the eighth plus 2 to the seventh is 384. So they're saying that the sum that we get, it's going to be greater than or equal to 2 to the eighth, but it's still going to be less than 2 to the ninth. So that means it's going to have a leading one in the 2 to the eighth spot. It's going to be like 2 to the eighth. Like if you represented it as a sum of powers of 2, 2 to the eighth would be the biggest power of 2 in the sum.
Right.
So you would have a leading one in the 2 to the eighth position. So this is a case where you would get overflow, because you'd have like an extra ninth digit on the left with a 1.
Right.
Um, so the procedure says that we'd have to truncate that one, but like now they show like why you can do that, and still get the right sum. So they say like, well, truncating that leading one is the same as subtracting 2 to the eighth from the number, because the leading one in the 2 to the eighth position means like that the number is the sum of 2 to the eighth and some other powers of 2. So truncating the leading one is the same as getting rid of the um is the same as subtracting 2 to the eighth. So then we can see what happens when we subtract 2 to the eighth. So the original sum is a plus 2 to the eighth minus b. Then we subtract 2 to the eighth from it. Then they rearrange 2 to the eighth plus a minus b minus 2 to the eighth. And then you have a 2 to the eighth minus a 2 to the eighth, so the 2 to the eighths go away. And you have a minus b. And a minus b is the same as a plus negative b. So that means that the sum that we calculated really is equal to a plus negative b, like we want.
Wait, so how did that go again?
Oh yeah, so I guess firstly, like the big picture idea is like we want to show that if you represent that negative number not just as itself, but if you represent it as 2 to the eighth minus b, and you add that to a, you still get you still get a plus negative b. It's still equal to the sum that you want. So instead of calculating a plus negative b, we calculated a plus 2 to the eighth minus b, because 2 to the eighth minus b is the representation of the negative number, negative b. So they showed that a plus 2 to the eighth minus b, they showed that that would have a leading 1 in the 2 to the eighth position. It would have overflow. Um, the procedure says that like after calculating that sum, you truncate the 1 in the 2 to the eighth position. So when so a plus negative b, it's calculated as a plus 2 to the eighth minus b. Then you calculate that and then you truncate the leading 1 minus 2 to the eighth. Um, and and then because truncating the leading 1, the overflow 1 there, it's in the 2 to the eighth position. So getting rid of that leading 1 is the same as subtracting a 2 to the eighth. Because if you have like a binary representation, all the one, like a binary representation in decimal is equal to like adding up all the powers of 2 that correspond to 1s in the binary representation. So if you have a 1 in the 2 to the eighth position, the number in decimal would be like 2 to the eighth plus some other powers of 2. So getting rid of the 1 in the 2 to the eighth position is the same as subtracting 2 to the eighth. So, so yeah, so we have
Well,
a plus negative b. Oh, go ahead.
oh no no. So are they saying that the formula matches up with the procedure of subtracting 2 to the eighth? Like I know in the
Mm,
procedure we subtract 2 to the eighth in the sense that we drop the leading 1 in the case of overflow.
yeah,
Are they
yeah,
saying
exactly.
somewhere in the formula the minus 2 to the eighth is the equivalent to that, or they're not saying that it matches up with the formula?
Oh, well, I think what they're doing is like they're applying the procedure and they're kind of showing like algebraically what are you doing when you do the procedure.
Mhm.
So they're pretty much doing the procedure, and and showing that when you do the procedure, you really do get a plus negative b, or you get something that's equal to a plus negative b.
Right. I want to understand this because they don't drop the leading 1 just as like a magic trick that happens to work, but it algebraically would make sense.
Yeah, yeah, exactly. Like algebraically, you have to do it actually to get the sum that you want.
You have to do it, yes, but it could still just be like a magic trick that happens to work. But not only do you have to do it to get the right answer, but um you can like see you can see it through the algebraic formula as well, right?
Yeah, yeah, exactly. Because like yeah, because it's like we want to calculate a plus negative b, but we're not just going to do a plus negative b. We're going to apply the procedure. So a, we just leave it as the binary representation of a. Negative b is negative, so we represent it as 2 to the eighth minus b. And then we showed that when you do a plus 2 to the eighth minus b, you get a leading 1 in the 2 to the eighth position. So continuing to follow with the procedure, we subtract a 2 to the eighth, which is equivalent to getting rid of the leading 1. Um, so we have a plus 2 to the eighth minus b minus 2 to the eighth. And then you end up having a 2 to the eighth minus 2 to the eighth, so that's 0. So you're left with a minus b, which is equal to a plus negative b.
Which is equal to a plus negative b.
Yeah, and that's what we wanted. We wanted to show that like when you apply the procedure, the result you get is in fact equal to a plus negative b.
Oh, okay, okay. So you're right. It is more like they're saying you have to subtract 2 to the eighth in order to get a plus minus b, a plus negative b.
Yeah,
But that
yeah,
is,
yeah. That's why it's there in the procedure. Yeah,
it's still kind of, I'm calling it magic tricky. Maybe I could use a better term, but like, it's, it's like a, it seems like it's like a trick. I, I,
yeah,
I guess it's just like a procedure type of thing. Maybe trying to do math using binary is just like that. Like you have to kind of um hmm, kind of have to create a custom procedure like dropping the leading bit like that in order to get it to fit correctly. So it's like a correct procedure. It's just like more custom than the algebra I'm used to.
Yeah.
I've never seen a step in the procedure added like that. Like, hmm,
Yeah.
it,
Yeah,
it,
it's
it
interesting.
it's like it doesn't seem like a mathematics step, but it obviously it has um it works out like
Yeah.
it works
Yeah, it
out
is interesting.
mathematically. It just doesn't seem like a mathematics step.
Yeah, well, yeah, kind of, yeah, in a way, yeah, I think it doesn't, yeah, because like you're calculating a sum and then you're just like getting rid of part of the sum and then like that gives you the
Right.
answer. Yeah, yeah. But I guess it does work based on the proof, like, and I guess maybe that's how people realized it, like, because,
Exactly.
yeah, because they realized that, like, if you, like, yeah, if we get that one, like, if we get that leading one, then that means we're adding a 2 to the eighth, and then, like, if we get rid of it, that gives us just a minus b.
Yeah.
Yeah, but it is interesting. Yeah, it's kind of like, yeah, it's just sort of a useful procedure for getting to the result we want.
Yeah. Hmm, interesting. Okay.
Yeah. Yeah, and then they give us an example of like doing it in practice.
Let's see example. Use 8-bit representation to compute 39 plus 25 plus negative 25. Okay,
Yeah.
so let's see. Negative 25, we'd want to get 25 and then turn it into its 2's complement.
Yeah. Yeah, exactly. So we need the binary representations using 8 bits for both of those numbers. And yeah, we'd use the two's complement of 25. That would be the representation of negative 25.
So yeah.
Yeah, and then like to get the 8-bit binary representations, we can think like 39, like what's the what's the biggest power of 2 that's less than or equal to that?
So for,
And yes,
let's see, for 39, I know for 25 we have 16 plus 8 plus 1.
yeah, yeah, yeah. So using that, so we can write that one in binary. Um, so I have a like a 1 on the far right.
And then I believe that's its 2's complement. I added the 1 in my head for 39.
Yeah. Oh, except so is let's see, it was 16 plus 8 plus 1. So those the double ones they'll be moved like one to the left because like so the one on the far right is the ones place, then they have the twos place to the left of that, then the fours place. So instead of a one in the fours place, we'll have a one in the eights place, and then the sixteens place.
You mean over here
So
whenever.
like the third like the second one so you have like 0 0 0 1 1
Oh, you're
0
right.
0 1. Yeah. So yeah, exactly. So the
So we have 16 plus 8 plus 1.
yeah. Yeah, so we have a 0 in the fours place and a 0 in the twos place and then a 1 in the ones place. Yeah. Yeah, and then flipping the bits.
If we add one, we get this. For 39, we have 32 plus 7. So we'll need to add 6 and 1. 1, 2, 4. Like so. Well, 4, 2, and 1, I believe.
Yeah, 32 plus 4. Yeah.
Okay, so we would be.
Yeah. So then we can add 39 plus negative 25. So we'd have the 0, 0, 1, 0, 0, 1, 1, 1 on top. And then 1, 1, 1, 0, 0, 1, 1, 1.
Okay. And then. So our procedure is just to add this together and, well, I guess at some point we would need to check to make sure it's within the range. I mean, I can see that it's within the range.
Yeah.
I can
Yeah, but
eyeball
we
it.
do need to if we end up with a ninth uh a ninth spot on the far left, then we trunk with a 1, then we truncate that 1.
And yes, we end up in that situation whenever we're. Is it whenever we're.
Well, it's when we get to like 128, something from what, or no, it's when we get to something like from 256 to like 511, I guess.
You would only get up there if you're dealing with negative numbers, right? Like a negative number minus another negative number. Well, a negative number minus a positive number could get you that high up. I think in one.
Yeah, well, I guess yeah, well, we're representing both the positive and negative numbers as positive numbers in a way, because like both of these binary representations in that sum would be represented like they would correspond to positive numbers in decimal notation if we kind of just went directly to decimal notation.
Hmm.
So it's kind of like we have something that's like in the range of 128 to 255, and then we're adding something else that's like less than 128, but non-negative. And that could be enough to get us beyond uh yeah, maybe it could be enough to get us like beyond 256, I guess.
Say that one more time. What would be enough to get us beyond 256?
Oh, so like the bottom number there, the one with the leading one. So the ones with the leading ones, those are from 128 to 255. Um, they're the representation of negative numbers. And then the thing on top has a leading 0, so it's something that's less, it's in the range of 0 to 127. Um, so we're taking like something in the range of 128 to 255 and adding something from 0 to 127. And I guess if the thing in the range from 128 to 255 is big enough, adding the smaller thing could be enough to get it to
I see.
256 or higher. Yeah, so we could end up with a leading 1 in the 2 to the 8th position.
So let me see. Like, there's two cases. There's one where our number is between um 255 and 128, and there's the other case in which we go above 255. Um,
Yeah. Yeah, like you could get above 255 if you're adding two numbers together, like you're adding something that's from 128 to 255, you add something else to it, maybe that's enough to get it to 256 or higher.
So let's say we have two different sums. One's 255, the other one's 257. In the 257 case, we would end up subtracting 2 to the 8th. So we'd end up with our answer being 1, right?
Uh, 255 plus, yeah, I guess so that would be like -1 plus -3. I guess that would be -4.
Like if we had two numbers that when you add them together, you get 257. So like,
Oh. Oh yeah.
but we're going to drop the leading one. We're going to truncate the the one and then the 2 to the ninth position.
Yeah.
And so the like raw representation of the binary number after we drop it would just be 1, I believe. If 257 was the original number with that overflow.
Yeah. Well, I guess. Oh yeah. Yeah. Oh yeah. It would be. Yeah. That's interesting.
So, but with 255, we wouldn't need to drop anything because there is no number. So it would be, well, it'd be 255, which is,
So that's the two's complement of 1, 2 to the 8th minus 1. So that means it's the representation of -1. So 255 would
right.
correspond to -1.
Whereas, right, right. Whereas I'm not sure what this one corresponds with when we drop when we subtract 2 to the 8th.
257.
Yeah.
Oh yeah. Yeah, I guess it does mean that we got a sum of 1. We had to apply the procedure dropping the leading
Oh,
1, and that showed us the sum was 1. Yeah. But yeah, it might end up happening with this sum that we're doing as well.
interesting. Sum of 1. I mean, I guess it's 1 greater than 256.
Yeah.
If we got 256, we get 0.
Yeah, exactly.
So when doing like binary addition with signed numbers, I guess if it overflows, you could just subtract 256 from whatever the answer was, and then that would get you the answer you're looking for.
Yeah.
And simply dropping 256 is the equivalent of subtracting it.
Yeah.
Yeah, simply dropping that bit.
Yeah, exactly. Yeah, because like when something is written in binary notation, like what it means is that the thing equals the sum of powers of 2 times the corresponding ones and zeros. So like if you have a 1 in the 2 to the 8th position, that means that the binary number, like it's equal to the sum of powers of 2, where one of those is 2 to the 8th. Like one, you have a 1 times 2 to the 8th in the sum. So if you get rid of that 1 and turn it into a 0, um, then it's like you don't have 2 to the 8th in the sum anymore, so it's like you're subtracting it.
Say that one more time.
Yeah, so like whenever you have a number written in binary, like what it means that, or at least like what it corresponds to in decimal notation is like um you're multiplying the ones that you're taking the sum of the ones and zeros multiplied by the corresponding powers of 2. The powers of 2 correspond to like their place, like whether they're in the ones place, the twos place, the fours place, etc. So like 110 by definition would be 1 times 2 squared plus 1 times 2 to the first plus 0 times 2 to the 0. Um, so yeah, like that's what they would be in that by definition if you wrote in decimal notation equal to. So So like if you have a 1 in the 2 to the 8th position, that means that the number in decimal notation would be equal to 1 times 2 to the 8th, because you have a 1 in the 2 to the 8th position, plus like something times 2 to the 7th, plus something times 2 to the 6th, etc. Depending on whether you have zeros and ones in those places.
Ah,
But like there's a 2 to the 8th in the sum, and so if you get rid of that 1 in that spot and like you have a 0 instead, it's like you subtracted the 2 to the 8th.
makes sense.
Yeah.
So let's see.
Yeah, so for this sum, we have on the far right 1 plus 1 gives us 1, 0.
Yeah, I'm just curious as to what the two's complement of the sum would be. Or I'm interested in the raw binary representation of the sum before you drop the 2 to the 8th position, assuming you have to drop it.
Yeah. Yeah, well it's kind of I don't know if it like has that much meaning. I guess it's like it's kind of it's like the real sum plus 2 to the 8th, I guess.
Yeah, I guess so. So let's see. You would have to get that number, you would need to first get the decimal representation of this binary number. Um, I guess that would be 2 to the 7.
Oh yeah, so that was negative 25.
Oh,
I guess we oh yeah, oh yeah, but to get the raw 1, yeah, that would be yeah, 1 plus 2 plus 4 plus uh plus 32 plus 64 plus 128.
okay.
So that would be a big number, but even if we just calculated the whole thing in binary, though, the sum, whatever the sum is, that would be then we could convert that to decimal.
1, 2, 4. Um, Say that one more time.
Um, we could also like, oh yeah, but we could do it this way as well. Like it would work either way. But we could also like if we calculated the sum in binary, then we could convert that to decimal.
Calculate the sum in binary. Yeah, I guess that's
Yeah,
true.
yeah, we can do this. We can convert each of them to decimal and then add them.
So let's see. So it's gonna give us 231.
31. So that wouldn't have a leading one, or that wouldn't have overflow.
Overflow. Well, if we added them, they give us 270, right?
Oh, right. Oh, yeah, because we're adding them. Oh, yeah, they would get, so there would be overflow. Oh, yeah.
It would overflow if 256 is 0, then we can just subtract this from 256 to get 14, right?
Yeah. And that's what we should get because we're doing 39 plus negative 25.
39 plus negative 25.
Like that's the original sum that we're calculating.
Okay, which is just like 39 plus 231 minus 256.
Yeah. Yeah, exactly. Yeah.
Interesting.
But yeah, now we can see how it works in binary. Um,
Right? Okay, so in binary, 0,
so in the rightmost column,
carry on, 0, carry on, 0, carry on, 1, 0, 0, carry on, 0, carry on, 0, and then drop
Oh yeah, I think
this. Hmm.
yeah, I think one thing though is that on the uh column like
Oh, this one. These.
yeah the two columns next to the one on the right, you have 1 plus 1 plus 1, that would be 1 1. So you end up with ones. Yeah. But yeah, we do have that leading one there, so then we can truncate it. Um, and then the answer is going to be 0 0 0 0 1 1 0. Yeah,
Interesting.
yeah. So yeah, it's pretty cool. It worked.
It did. It was a little quicker doing it in binary that time, but I think the importance here is probably figuring out how to do math using binary because in like a circuit situation, the addition would be done with basically a binary representation since you have like gates which work in ones and zeros. You have to essentially AND them together. But from what we learned in the adder circuit lesson, to add numbers, uh, we need to think about them in terms of binary to add them using
Yeah,
hardware.
yeah, exactly. Yeah, so I think this method was designed, yeah, because it's convenient, like for computers to do.
Yes.
Yeah, because I guess computers like represent things with bits, and then each bit can have one of two values. So it's nice to represent numbers in binary because then you can have one of the two bit states correspond to one, and the other one correspond to zero.
Mm-hmm. Hmm. Let's see here. So we learned how to add simple numbers. Now I guess we're learning the concept behind adding like more complex numbers. Well, we learned how to add first. I guess now we're really just learning how to deal with negative numbers and in signed addition.
Yeah, yeah, exactly.
Okay.
Yeah, yeah, and then we can see case four, and that's the last one where both integers are negative.
Integers are negative. So let's see. This case involves adding two negative integers in the range -1 through 128, whose sum is also in this range. So consider the sum -a plus -b, where a, b, and a plus b are all in the range 1 through 128. In this case, the 8-bit representation of -a and -b are the 8-bit representations of 2 to the 8th minus a and 2 to the 8th minus b. So if the 8-bit representation of -a and -b are added, the result is 2 to the 8 minus a plus 2 to the 8 minus b, which equals 2 to the 8 minus a plus b plus 2 to the 8. Right. So recall that truncating a leading one in the ninth 2 to the 8th position of a binary number is equivalent to subtracting 2 to the 8th. So when the leading one is truncated from 8-bit representation of 2 to the a minus a plus 2 to the 8 minus b, the result is 2 to the 8 minus a plus b. Makes sense. Which is the 8-bit representation of -a plus b, or -a plus -b. So let's see here. 2 to the 8 minus a plus b is the 8-bit representation. Well, I see that 2 to the 8th minus a plus b is the 2's. I see it's a 2's complement of a plus b. I guess that's why it's -a plus b.
Yeah, because a plus b is the absolute value of negative a plus b, because a and b are both positive.
Yeah, which is equal to negative a plus negative b. Exercise 37, you're asked to show that the sum 2 to the 8th minus a plus 2 to the 8th minus b has a leading 1 in the ninth 2 to the 8th position.
Yeah, because we needed that part because like they subtracted 2 to the 8th, and for that to, like according to the procedure though, you can only do that when you have leading 1 in the 2 to the 8th position, and they didn't actually show that. They kind of leave it for the reader to do that.
Okay.
Yeah, and I guess like we could kind of informally like see why, I guess, because like we have 2 to the 8th and then we're subtracting a plus b, and a plus b like so negative a and negative b are from negative 1 to negative 128. That means a and b, like their absolute values, are in the range of 1 to 128. So we're taking 2 to the 8th, 256, and we're subtracting the sum of some things in the range of 1 to 128. So that could be as small as 2, if a and b are both 1. It could be as big as 2 to the 8th if a and b are both 128, because then 128 plus 128 is 256. So 2 to the 8th minus a plus b is going to be something from um or no, yeah, it could be something from it could be 0 all the way up to 254, um 254 if a and b are both 1, because we know they have to both be positive. They can't, neither of them can be 0. So the minimum possible is if they're both 1. So we're taking 2 to the 8th minus a plus b is something from 0 to 254. Then we're adding 2 to the 8th to that. Um, well, that's not going to get us all the way to 2 to the ninth, because 2 to the 8th minus a plus b is less than 2 to the 8th. Or 2 to the 8th minus a plus b, yeah, it's less than 2 to the 8th. So 2 to the 8th plus 2 to the 8th would get us to 2 times 2 to the 8th, or 2 to the ninth. So we have 2 to the 8th and we're adding something less than 2 to the 8th. So that's going to be in the range. It's going to be between 2 to the 8th and 2 to the ninth, but less than 2 to the ninth. So that means that it's going to have a leading 1 in the 2 to the 8th position, because 2 to the 8th is going to be the biggest power of 2 that's less than or equal to it.
So let's see. If there's a 1 and a 2 to the 8th position, then we have to drop it, right?
Yeah, exactly. And yeah, and they like they just kind of say that there's a leading 1 in the 2 to the 8th position, but then they kind of ask us to prove that there's a leading 1 in the 2 to the 8th position, and that's
And so,
the sum that's kind of in between the paragraphs.
and then how did you?
Yeah. Oh yeah, so to prove it, like so we have 2 to the 8th minus a plus b plus 2 to the 8th, and we want to show that if we put that in binary, we'd have a leading 1 in the 2 to the 8th position.
Wait a second.
Um
Are you starting from here? You said 2 to the 8th minus a plus b plus 2 to the 8th.
yeah.
Okay.
Yeah. Yeah, because that's equal. Like if we apply the procedure, like a and b are both negative, so to add them, we're going to add their the two's complements of their absolute, or sorry, negative a and negative b are both negative. So if we want to add them,
Right.
following the procedure, we add the two's complements of their absolute value, and then they just rearranged it in a convenient form, 2 to the 8th minus a plus b plus 2 to the 8th. And then the next step in the proof is they just assume that there's a leading 1 in the 2 to the 8th position and then go from there. But then we need to show why is there a leading 1 in the 2 to the 8th position of that number in binary. And the reason why, like, firstly, we can think like, uh, what are the numbers that have a leading 1 in the 2 to the 8th position? Well, 2 to the 8th does. And in fact, anything from 2 to the 8th, like 2 to the 8th, and then anything beyond that, all the way up, uh, or anything that's greater than or equal to 2 to the 8th, but less than 2 to the ninth, will have a leading 1 in the 2 to the 8th position. Because, like, a leading 1 is like the leftmost one in the whole number in binary. So a leading one kind of corresponds to the greatest power of two that's less than or equal to the number.
Right.
So yeah, exactly. So anything that's uh like any x such that 2 to the eighth is less than or equal to x is less than to the ninth, um, will have a leading one uh in that position, the 2 to the eighth position. So pretty much we want numbers from 256 to 511.
Right.
Because 512 is 2 to the ninth. So anything from 256 to 511 is going to have a leading one in the 2 to the eighth position. And we need to show that this number, 2 to the eighth minus a plus b plus 2 to the eighth, is in that range. It's something from 256 to 511.
How do you know that a plus
And
b is less than 2 to the eighth?
uh, we don't know that it's less than it, but we know that it's less than or equal to 2 to the eighth, because it could be equal to 2 to the eighth because we have that a and b are numbers from 1 to 128. Um, or actually, sorry. Oh yeah, we do actually know it's less than 2 to or yeah, we do know it's less than 2 to the eighth. So yeah, I was wrong. You're right about that because like they say that they assume a plus b is in the range 1 through 1 through 128. So 2 to the eighth minus something that's in the range of 1 to 128 is going to be less than 2 to the eighth.
They assume the sum is below 128.
Yeah, because like according to the procedure, like we can only apply this procedure if the things that we're adding are in the proper range and if the sum is in the proper range. So um the range is negative one, the full range is negative 128 to 127. That's where we're allowed to be following the procedure. If we have negative numbers, their sum is going to be in in the negative part of that range. If we're adding two negative numbers, so we know their sum is going to be something from -1 to -128. Um, and the a and b are the absolute values of the negative numbers. So their sum is going to be in the range of +1 to +128. Um, so the 2 to
Oh,
the eighth minus a plus b. Oh god.
oh well, 128 is less than 2 to the eighth, right?
Yeah, it is. So like the biggest the sum could possibly be is 128. And so we're taking 2 to the eighth, and we're subtracting a positive number that's at most 128. That's going to be just something less than 2 to the eighth. Some positive number less than 2 to the eighth.
So in that formula, isn't that equivalent to 2 to the ninth minus a plus b? So we have 2 to the eighth plus 2 to the eighth, which is like 2 to the eighth times 2.
Yeah, yeah. Well, yeah, you're right. Yeah, 2 to the eighth, 2 to the ninth minus a plus b. And if we have 2 to the ninth, minus something that's from 1 to 128, um, that is in fact going to be in the range of like because like 2 to the eighth is 256 and 2 to the ninth is 512. So if you take 512 and you subtract something from 1 to 128,
Right.
and yeah, it'll be between 256 and 311 and 511. So that means it'll have a leading one in the 2 to the eighth position.
Right. The only way you could get under 2 to the eighth from 2 to the ninth is if you were to subtract at least 2 to the eighth.
Yeah, exactly.
Okay.
Yeah. Yeah, so that's interesting. Yeah, and in that case completes the proof.
That there will be, yeah, I guess that would complete the proof.
Yeah, because they covered all possible combinations, like they're both negative. You're adding two negatives, you're adding two non-negatives, and they also covered like if you're adding a negative and a non-negative.
So let's see. Okay. So then how is this example supposed to exercise what we just learned here?
Well, I guess it's kind of like it's kind of giving us practice with the procedure, I guess. It doesn't really exercise like the theoretical explanations and the proof.
Yeah,
There's more practice. So with a case where both integers are negative, I guess it's just because like case four, we were looking at both integers being negative, and now and they just gave us an example of like doing the computation when they're both negative.
I see.
Yeah. So we got to start out by finding the 8-bit representations of both of them, which will be the two's complements of their absolute values.
Right. So we have
Yeah. So first we got to find what the absolute values would be in binary notation.
so for 89, we would have 64 plus 25 and get
Yeah, and then 25 would be 16.
like
And
this,
then
right?
yeah. Yeah, exactly.
Let's see here.
Yeah, then zeros everywhere else.
And then for 25, we would have one here. Oh, 25. It's the same thing.
Yeah, 16 plus 8 plus 1. Yeah, and then we can fill in the zeros. That'll give us the 8-bit binary representations.
To get negative.
Yeah. Yeah, now we gotta do the two's complements of those, so we flip the bits.
And then you add 1.
Yeah. Yeah. And then that 0 turns into a 1. Yeah.
So now, if we want to add these, I guess I could just. So we have
Yeah.
0, which should get us 8 plus 4 plus 2, 13.
Let's see. Um,
That shouldn't be right.
I guess we um wait, let me double check the so 1 0 here 1 1 here 1 1 1 0. Oh, we do have a 1 in the next to that leading 1. We'll also have a 1. Oh wait, no. Yeah. Because in the 2 to the 7th position next to the 1 with the square, there'd also be a 1 because a couple
Oh,
columns
no.
earlier we had 1 plus 1 carry a 1, 1 plus 1 carry a 1, and then 1 plus 1 plus 1. So we actually have 13 plus 128. But
So,
in fact, we actually still need to do something because so we have something 1 0 0 0 1 1 1 0. It has a leading 1, so that means it represents a negative number. And that means that to find like what this is in binary, we need to take the two's complement of it and then add a negative.
Interesting.
Yeah, because what we have here is the two's complement of the absolute value of our answer.
True. So let's see, we would have,
Yeah, so I gotta flip the bits and then add one.
I think it's like this,
Yeah,
which would be, so we have 96 plus 16. So it's 112, and then plus 2, so 114.
yeah. So that's the absolute value of the answer, and the answer is negative, so then I just put a negative in front of that. Negative 114.
Wow,
Yeah, that's cool.
that is cool. I noticed that before we took the two's complement, we had 13 as the answer.
Yeah, although I guess technically, well, we had 13 plus 128 because we had also the 1 and the 2 to the 8th to the 7th place.
True. You might say
So we had,
it's like, yeah, I guess that'd be negative 13 in one view. But, huh, interesting.
yeah, or but we had the leading one that we truncated. We also had another leading, even when we truncate that, we had another leading one in the 2 to the 7th position, which
Right.
is 128. So we have like 128 plus 16 plus 4 plus 2, which would be
Or it was 128 plus
one.
8 plus 4 plus 2?
Uh, oh, right, 8 plus 4 plus 2, yeah, which was one would be 142. So 142 is like the raw decimal version of the two's comp of or like the decimal version corresponding to the binary representation that we're using for this negative number.
Yeah. In terms of shortcuts, I guess that would also be represented as negative 13 because the leftmost digit is the sign.
Yeah, but we have two leftmost ones. So if we drop one of them, we still have another leftmost one that isn't the sign.
Oh, wait, is that not the sign?
Well, the one in the box is, but the one in the circle isn't. Or I guess wait, oh sorry. Yeah, you're right. The one is the sign. The circled one is the sign in the sense that it tells you that the number is negative. But in terms of um like it wouldn't correspond to negative 13 though, because like the negative in terms of like figuring out what the negative that it corresponds to, that would be negative 114.
Negative 114. Oh, yeah, 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 you're right.
Yeah, because you got to do the two's complement to figure out what it is like represented as a negative. If you represented it, if you just like kind of just took the 100001110 and represented that in decimal, then you would get 142.
Right.
Yeah,
142. Hmm. Yeah. I think it's just a coincidence that negative 13 and negative 114 are so similar, but I don't think that there's some easy way to go from one to the other. Easier than just getting the two's complement.
yeah, yeah. It might just be a coincidence in this case.
Yeah.
Yeah,
So let's see. You want to like in there and do hexadecimal notation next time?
Uh, yeah, either way is good. Yeah, the hexadecimal, it'll be more straightforward. Because yeah, that one, I think for hexadecimal, like they don't do all the complicated stuff. They just like say like what it is and how to convert one from one way to the other.
Hmm. I guess we could do it today if you'd like.
Yeah, and maybe we could quickly do it.
All right, let's see. Hexadecimal notation. It should now be obvious that numbers written in binary notation take up much more space than numbers written in decimal notation. Yet many aspects of computer operation can best be analyzed using binary notation. Hexadecimal notation is even more compact than decimal notation, and is much easier to convert back and forth between hex and binary notation than it is between binary and decimal notation. That's good to know. The word hexadecimal comes from the Greek root hex, meaning 6, and the Latin root deci, meaning 10. Hence, hexadecimal refers to 16, and hexadecimal notation is also called base 16 notation. Hexadecimal notation is based on the fact that any integer can be uniquely expressed as a sum of numbers of the form d times 16 to the nth, where each n is a non-negative integer and each d is one of the integers from 0 to 15. In order to avoid ambiguity, each hexadecimal digit must be represented by a single symbol. The integers 10 through 15 are represented by the symbols A, B, C, D, E, and F. The 16 decimal digits are shown in Table 253, together with their decimal equivalents, and for future reference, their 4-bit binary equivalents.
Yeah,
Interesting.
yeah. So the idea is kind of like the same as binary and decimal. Like in binary, we have two digits, 0 and 1, and then each place in the number it corresponds to a power of 2, 1, 2, 4, 8, etc. And then in decimal notation, we have 10 digits, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and each place corresponds to a power of 10, 1, 10, 100, 1,000. And then in hexadecimal notation, we have 16 digits, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then A, B, C, D, E, F. And then each place in the number corresponds to a power of 16. So we'll have 1, 16, 16 squared, 16 cubed, etc.
Interesting.
Yeah. And these will end up being shorter, like have fewer digits than things written in decimal or binary notation.
Hmm. Let's see if it's actually easier to convert between hex and decimal than binary and decimal, though. And if it is, I wonder why.
Yeah, I don't know why. Yeah, I'm curious.
It says convert 3CF to decimal notation. Okay, well, 3CF. So F is 15.
Yeah. So it's gonna be 15 times 1. It's in the ones place.
This is going to be 12 times
Yeah,
16, and then 3 times
yeah,
16.
yeah, yeah. 3 times 16 squared.
Yeah.
Yeah, yeah. I can do that one on a calculator. 3 times 16 times 16. So we have 768 plus 192
I wonder.
plus 15. So it looks like it's 975.
Let's see here. Yeah. Because you had 48 here. Wait, no, no. You're right. It's
Um,
I gotta get used to this. So let's see here.
yeah, you'd have like 3 times 16 times 16 plus 12 times 16 plus 15. And 3 times 16 times 16 is 768. 12 times 16 is 48. And then add 50. Oh, wait, no. 12 times 16 is 192.
Interesting. I get this based on the formula that they gave us that in that 16 squared place. The formula, I think it was it d times 16 to the n?
Yeah. Yeah, so it's like kind of like for binary, it's like the same idea as binary, but with like each place corresponding to a power of 16. So the rightmost place is 16 to the 0 power, so it's the ones place. Then to the left of that, you have the 16s place. Then to the left of that, you have the 16 squared place, and then the 16 cubed place, and 16 to the fourth power place, etc. Um, so what this would be is like you multiply each digit by the corresponding power of 16 and then add the results.
Interesting.
Yeah, so you'd have like 3 times 16 times 16 plus d corresponds to 13, so it's plus 13 uh, times 16. Oh yeah, so 13 times 16, and then f corresponds to 15, so it's plus 15 times 1.
Like this one is more apparent with hex than it was with decimal. I guess because with decimal you're just multiplying it by 2. So you don't even
Yeah,
realize this step. But when any number
yeah,
other than 2, you do. You kind of write it out more.
yeah, exactly. Oh, yeah, and actually, sorry, I meant c corresponds to 12 rather than 13.
C corresponds to 12.
Yeah. So yeah, 768 is 3 times 16 times 16. And then 12 times 16 is 192. So you'd add 192 to that. 192 plus 1 plus 768. And then plus 15. Because that's what the F corresponds to.
Nice. What is this?
Yeah. Yeah. And then they show like going from the other way, hexadecimal, or they're going a different from hexadecimal to binary actually. And I guess they first like kind of show an example to illustrate the procedure, and then they have us do it. So I guess we could uh, see what they do in that example. Because one way of going from hexadecimal to binary would just be to go from hexadecimal to decimal and then from decimal to binary. But they have a different way of doing it.
Let's see.
So I guess the number is um, C50A. And then when I go from that to binary, um, so the A is in the ones place, 16 to the 0 power. The 0 is in the 16's place. The 5 is in the 16 squared place. 16 squared, so 16 is 2 to the 4th, so 16 squared is 2 to the 4th times 2 to the 4th, which is 2 to the 8th, 256. And then 16 cubed happens to be 4,096.
Let's see. So, did we already analyze the procedure here? Is it?
Not yet. Um, so well, I guess the first step is like you have the number in hexadecimal C50A, and then you see like what place is each of those in. A is in the ones place, 0 is in the 16s place. 5 is in the 16 squared place, where 16 squared is 256. So that's what 5 will be multiplied by. And then C is in the 16 cubed place, where 16 cubed equals 5,000, or no, 4,096. And then they just converted the letters to the decimal equivalents to make it easier. So C is corresponding to 12, A is 10, corresponds to 10.
Hmm.
Um, so then you gotta multiply those each digit by the corresponding power of 16 and add. So first, 10 is in the ones place, so it's 10 times 16 to the 0, or 10 times 1. And they, instead of doing 10 times 1, they do 2 cubed plus 2 times 1. I don't know why yet. 10 is 2 cubed plus, I guess they, so part of the procedure looks like each digit they rewrite it as a sum of powers of 2. So the 10, if you write 10 as a sum of powers of 2, it's 2 cubed plus 2. Um,
Is that all you have to do and you're done?
um, uh, I hadn't seen the whole thing. Let's see. Um,
It says
so we're,
juxtapose the results.
wow, really? Wow. That's cool. So they kind of prove that it works, and then, and so you just, wow. You write each hexadecimal digit in 4-bit binary notation. Oh, and then you just like put them side by side, and wow, that's interesting.
I wonder why this works.
Yeah. So I think the thing above is like sort of a mini illustration of why it works. Um, or wait,
Each digit in hexadecimal is a power of 16, right? So I just
yeah,
wonder how is that power being maintained in this binary representation?
yeah. Uh, well, yeah. Well, I guess so. On the rightmost thing, the A there. Well, A. I think I see. So okay. So what the hexadecimal notation means, like you take the digits and multiply them by the corresponding powers of 16. So the rightmost digit, you'll multiply it by 1. So that and also all of the digits can be written with 4, can be written in binary notation with just 4 bits, because all of the digits, some are from 0 to 15, and you can write anything from 0 to 15 with 4 bits. Once you get to 16, you need a 5th bit. So
Hmm.
so the rightmost digit, it's multiplied by 1. So you're just going to be, you can just take that digit as it is. That's going to be part of the sum, and it's on the right. Um, the second digit is multiplied by 16, and if you move it to the right, like to the left like that, that actually is 16 times the digit, because um, like um, you're moving it 4 powers of 2 to the right, so every digit of that 0, you can imagine it being something other than 0, but like every digit of that 0 is going to be multiplied by 16. Like if you had, if instead of 0 you had 1111, and you put the 1111 there in that spot where the 0 is, then that's equivalent to multiplying every digit of the 1111 by 16, because you're moving every digit 4 powers of 2 uh, to the left, and 2 to the fourth is 16. So like the rightmost one, originally it was in the ones place, now it's in the 16s place. So you're doing 1 times 16. The next one to the left of that, originally it was in the
Oh,
um yeah, it was originally in the twos place, now it's in the 32s place, so it's multiplied by 16. So that corresponds to like multiplying by 16, which is what you're doing in hexadecimal. And then similarly, like the where the 5 is, that's in the 16 squared place, and putting the 5 in that position is equivalent to multiplying every digit of it by 16 squared, um, or multiplying the whole thing by 16 squared. And then the C, it's in a position such that you're multiplying everything in it by 16 to the 16 cubed. So like you're multiplying it by 16 cubed, which is what you're supposed to do with um when you're doing hexadecimal.
whoa. And then like the three digits to the left of the rightmost digit in each of these nibbles.
Yeah.
I wonder how that works out so well.
Yeah, well, I think it's because like so every digit um is like it has been like for example looking at the 0, um uh every digit of it has been moved 4 spots to the left. Um, so that means that it's in a spot that corresponds to a power of 2 where the exponent is 4 greater. Um, so like 0, 0, 0, 0, just by itself, you have we have the rightmost 0 in the 1 spot, the next one in the 2s, the next in the 4s, the next one in the 8ths. If you shift it to the left like that, you're going to have the rightmost 0 in the 16 spot, the next one in the 32 spot, the next one in the 64 spot, and the next one in the 128 spot. Um, each spot, it's 4 spots to the left of where it was, where it would be just kind of writing it by itself. So it's been every spot has been shifted 4 spots to the left, and shifting 4 spots to the left means that
You
it's in a
increased by a
spot
power of
corresponding.
16.
Yeah, exactly. Yeah, you're in a power of you have each spot corresponds to a power of 2, so you're increasing the exponent on the 2 by 4, so you're multiplying by 16. So you're actually multiplying each digit by 16. So you're multiplying the whole thing by 16.
But
And then similarly with 16 squared and cubed.
ignoring all, all of these shifts to left, what about in the first nibble, like the rightmost nibble, the three digits, the three leftmost digits,
The 110,
the
or
the
if each oh, those ones. Oh yeah, so those ones so the A there, that's the rightmost digit of the hexadecimal number. Um, so 1010, that's the binary representation of the rightmost digit of the hexadecimal number. Um, and that the rightmost digit is multiplied by 1, so you can just write it as is at the far right.
interesting.
Meaning that because like if you wrote it by itself, you would just have 1010. And if you're putting it there, 1010 on the far right, that's 1010. Like you're not shifting it at all, so you just have the original number as part of the sum.
Interesting.
And that's what you want because it was the rightmost digit of the hexadecimal, so it's multiplied by 1.
It's like, huh.
Yeah, because what this really is like this is a times 1, because a is 1010, plus 0 times 16 plus 5 times 16 squared. Because the 5, all of its digits were shifted 8 units to the left, um, which is equivalent to multiplying them by 16 squared because that's 2 to the 8th. And then C, that's in that position, you really have c times 16 cubed, because every digit of c has been shifted to the left by 12 units.
Right.
That's 2 to the fourth cubed, which is 16 cubed.
Right. Yeah, I guess just the interesting thing is shifting these intermediate digits to the left. Um it's just neat how that maintains its increase by a power of 16.
Yeah, although the 1010, none of those digits necessarily need to increase by a power of 16, because like we had C50A, so that's A times 1 plus 0 times 16 plus 5 times 16 squared plus C times 16 cubed. Um, and A, the binary representation of it is 1010. And if you have just one, so 1010 equals A. So when we have 1010 there on the far right, that's just A. You're not increasing it by a factor of anything because you're not shifting it you're not moving the digits to be at higher spots or further to the left. So every digit is where it was in the original A. So that means like you just have plain A as part of the sum.
Yeah, I guess what I meant, like, so in general, like if you have a binary number like this binary number here, or rather, if you have a binary number, the positions in these first four positions, like whatever value you have here, if you were to shift them over by 4, then they would all increase by a power of 16, right? So like if you had one here,
Yeah,
if you had yeah, one here, it'd be 16 here. Or if this entire
yeah,
number, right, if this entire number was equal to 2, it would be equal to, I think it would be 32 when you shift it over.
yeah, yeah, it would.
And even the power shifting applies to the individual numbers that are summed up to equal this large box. So, like, if you had a 1 here and you shifted it over, you would have a 16 here. If you had
Yeah,
your 2 here, it would be 32 here, so on and so
yeah,
forth.
yeah. Although technically, I guess instead of a 2, you would have 2 times 2. As you have in each spot you've got a digit multiplied by, oh yeah, but yeah, you could have a 2 in the sense that you have like a 1 times a 2. Yeah, because like in each
Exactly.
spot you have a digit times the power of 2. So,
Yeah, I mean, like if you had a 1 there, which would
oh
be,
yeah, 1 times 2, yeah. Yeah, exactly, it would become 32.
yeah,
Yeah, and if you multiply all the digits by 16, that's the same as multiplying the whole number times 16, because the number is equal to like a sum, and you multiply each part of the sum by 16, then you multiply the whole thing by 16.
right. And that's kind of what I've been looking at, multiplying these like components of the sum by 16. And if you multiply all the components of the sum by 16, it's like multiplying the whole sum by 16.
Yeah,
And you're multiplying it by 16 whenever you move it over 4 times in binary notation. Hmm.
Yeah. Yeah, that's really cool.
Yes. So let's see. Converting from
Yeah,
hex to
yeah.
binary.
Yeah, then they have us do an example, yeah.
Okay.
Yeah, so we gotta follow the procedure. I guess we first uh gotta rewrite the letters as decimal numbers. Um
Right.
and and then once we've got all of the digits as decimal numbers, then write them as binary numbers using 4 bits, and then put them side by side in the order that they appear.
So 15 is going to be all ones.
Yeah.
9 is going to be, let's see, 1, 2, 4, 8, and 1, 0. And then B is 11. So we need 8 and 3. So it'd be like this, I think. Yeah. That
Yeah.
is pretty straightforward.
Yeah. Yeah, that's really cool. Yeah, and then they give us a procedure to go the other way from binary to hexadecimal.
It's probably also kind of straightforward if you go through decimal first.
Yeah, but this will actually be easier.
Let's see. To convert from binary to hex, reverse the steps of the previous procedure. To convert an integer from binary to hex, group the digits of binary number into sets of 4, starting from the right and adding leading zeros as needed. Convert the binary numbers in each set of 4 into hex digits. That step always requires me to go to decimal first. Juxtapose those hexadecimal digits.
Yeah, yeah, I would have to do that.
So we got,
Yeah. So now we can go like, I guess,
oh, we go,
right, yeah, we go right to left. Uh, oh yeah, I guess it'll be right to left though, because then otherwise,
so you can add a 0.
yeah,
So this one's going to be 9, 10, 13, 4. So that would be
yeah.
4.
I think that's DA, D for 13 and A for 10.
4DA9. Nice.
Yeah,
We're getting a memory dump. So, smallest addressable memory unit on most computers is 1 byte, or 8 bits. In some debugging operations, a dump is made of memory contents. That is, the contents of each memory location are displayed or printed out in order. To save space and make the output easier on the eye, the hexadecimal versions of the memory content are given, rather than the binary representations. Suppose, for example, that a segment of the memory dump looks like this. What is the actual content of the 4 memory locations?
yeah. So I
Okay.
guess that means that like each 2-digit segment is in the computer, it's actually represented as something in binary.
Whoa. So I don't think binary would really help us though. Like a decimal representation might be useful for a human. But
Yeah,
okay. I guess it could be useful if those binary representations are like I don't know, instructions or inputs to a circuit or something.
Yeah, exactly. Because I think they're like when they say what is the actual content, they kind of mean like what is it actually stored in the computer as, and it's stored in the computer in binary.
Okay, so
So we got to do A3, and I think these are like four separate numbers. So A3, um,
okay. So A is 10, and we know that that is 8 and 2. 3 is 3, which is like this. B is 11, so that's going to be 8 and 3. 5 is going to be 4 and 1. 9 is going to be 8 and 1. 2 is like this. E is 14, which is going to be 8, 4, and 2. Okay.
yeah,
Yes. Oh, this is way easier. Oh, it's already over.
yeah, yeah,
Let's
yeah. So, and actually the end of the entire chapter.
really.
Yeah, yeah. So that's a big
Wow.
milestone.
It is a huge milestone. Okay, we can do these. Test yourself. Uh-oh. Well, let's see here. To represent a non-negative integer in binary notation means to write it as a sum of products of the form where.
So I think it's like d times 2 to the n, where d equals 0 or 1, maybe. Because I guess you have like what the binary representation really represents is like a sum of ones and zeros multiplied by powers of 2 corresponding to where they are and then
Right.
the number. So maybe that's what they. Oh yeah, so yeah, d times 2 to the n where d equals 0 or d equals 1. And then the other thing they say is n is a non-negative integer, which I guess is only non-negative powers of 2 because we have 2 to the 0, 2 to the 1, 2 squared, etc. But we don't have like 2 to the negative 1 or anything like that.
So where d is greater than or equal to 0?
Where d equals 0 or 1. Because d is like the d's are like the digits that we're multiplying by powers of 2, and then those digits are either 0 or
Ah,
1. So yeah, d equals 0 or d equals 1. Yeah, and then I just checked, and one other thing I guess they include, like just to be technical, is that like when we have d times 2 to the n, n is a non-negative integer.
right. A non-negative integer. D is 0 or 1 and is a non-negative integer.
Yeah,
Oh, I could say um
yeah. I could also say like n is an element of z, like the set of integers,
oh, it's just C.
and n is greater than 0, or n is greater than or equal to 0. Yeah, oh yeah. So that's an even more compact way of saying it. Yeah,
Um how do
yeah.
you do n in this notation?
Uh, I guess you could just write the word and I guess you could also use like the conjunction symbol.
Okay.
Yeah.
There's not like a pipe or anything specific to this. You add in, you use these conjunctions. Let's see.
Yeah. Yeah, well, I guess if you wanted to do a pipe, you could say like n is an element of uh the set of things that are in the integers such that they're greater than zero. But this is like this is more compact.
Let's see. It's greater than or equal to zero, right?
Yeah. Yeah, greater than or equal to zero.
Let's see. To add integers in binary notation, you use the fact that 1 in binary plus 1 in binary equals, and 1 plus 1 plus 1 equals.
Well, S one plus one will be one zero. And then one plus one would be one one.
You think that's the answer they're looking for?
Uh yeah, yeah, I think so. Because like when we're adding, like we those are the cases when we carry a one. So you end up with like if you have one plus one, then you put a zero in the column, and then you carry a one because it's one zero. And then if you carried a one and the carried one is above a one and a one, then you have one plus one, which is one one. So you put a one in the column and then carry the leftmost one. So yeah, you're using those results.
I wonder what about the way they asked it let you know that that's the kind of answer they're looking for and not simply 2 and 3.
Uh, well, I guess yeah, they are two and three, but I think like you're concerned with what they are in binary. I guess the fact that they put the subscript two indicates that they're looking for answers in binary.
Interesting.
Yeah, we're kind of suggestive because like knowing that one plus one is two, I guess wouldn't be as useful if you're adding in binary notation. Oh yeah, because I guess they say like adding in binary notation, so like rather than converting to decimal.
It says to add integers in binary notation, you use the facts that it's just that wording is not as clear as saying what's the binary representation of these sums.
Yeah, yeah, it could have been easier. Yeah, it could have done it better, but I guess it's like when you're adding any integers in binary notation, these facts are useful, I guess is what they're getting at.
Maybe
It's
so.
like yeah, like in an individual column, you could end up with one plus one, and they use the fact that that's one zero. You carry the one, and then you could when you carry a one, you could have it above two other ones, and then you end up with one plus one plus one. So I guess the idea is just like these facts are particularly useful when you're adding any binary integers.
Huh. I never thought of those answers that I gave there as facts, but I could see that being the case.
Yeah, yeah, I guess they're facts in the sense that they're just like things that are true about numbers in binary notation.
Yeah. Okay. To subtract integers in binary notation, use the fact that 10 in binary minus 1 in binary would be, well, oh, wait a second. That's not 10. So that would
A one
be,
zero. So I guess that's gonna be one.
right.
Yeah.
A half adder is a digital logic circuit that, a full adder is a digital logic circuit that,
I forgot what the difference was. I know they add things.
did a half adder use something? And I wonder, there was a reason why they called it half adder and why they called it full adder.
Yeah, the half adder kind of is like it does less and it's like a step in the process of the full adder. Like a full adder, I think includes multiple half adders or something like that. Um, I can
And
double check here.
there's something with truth tables.
Yeah. Oh, I see. Yeah, well, I just looked it up. I guess a half adder adds two binary digits, and a full adder um adds three binary digits, it looks like.
Really? A full adder doesn't add like an infinite amount of binary digits?
Hmm, I
Or
guess
would that
maybe
just be
not, I guess.
that'd be a combination of full and half adders?
Yeah, I guess so.
Oh. The 8-bit 2's complement of a positive integer a is, I believe it's 2 to the 8 minus a, isn't it?
Yeah. Yeah, like the binary representation of 2 to the eighth minus a using 8 bits.
Okay. To find the 8-bit 2's complement of a positive integer a that is at most 255, you. So we
I guess
can,
you write it in. Go ahead.
oh, positive integer a. Yeah, I guess you write it in binary, flip the bits, and then add one, right?
Yeah.
Okay. If a is an integer with negative 128 less than or equal to a less than or equal to 127, the 8-bit representation of a is blank if a is greater than or equal to 0 and is blank if a is less than 0. So
Well,
if a is within the range of negative 128 and 127, the 8-bit representation of a, huh,
yeah, well, if it's not, if a is non-negative, you just kind of do the usual binary representation using 8 bits. But yeah, I see in the book they say for this blank, the 8-bit binary representation of a is they fill in the blank with the 8-bit binary representation of a. That's kind of redundant. Oh
um,
wait, they say the 8-bit binary representation of a, so they add the word binary. But I guess the idea is you just do the usual binary representation of a using 8 bits. So I guess you could say like the binary representation of a using 8 bits or something.
okay. So if it's less than 0, it's not the 8-bit binary representation of a.
Yeah, it would be the
Is it the 7-bit?
binary representation.
Wait, no, no. Let's think. Um,
Yeah, like if a is negative, you use a two's complement.
right.
So it would be like the 8-bit binary representation of 2 to the eighth minus the absolute value of a,
I gotta
which would be the
remember
two's complement of the absolute value.
when you take the two's complement of a negative number, do you take it with the leftmost bit as
Mm,
well?
well, I guess I guess they kind of they take instead of they don't take I think it's rather than taking the two's complement of the negative number, they take the two's complement of the absolute value. So it's like the corresponding positive number.
Right. So let's see. If a is negative, well, if a is an integer within the range, The 8-bit representation of A is blank if it's negative.
Yeah, so I guess it'd be the 8-bit binary representation of
The
2 to the
absolute
8th
value.
minus the absolute value of A.
Okay.
Yeah, also the book in the answers has a typo. They say it's the 8-bit binary representation of 2 to the 8th minus A. It should be 2 to the 8th minus the absolute value of A.
2 to the 8th. Well, I guess it would be 2 to the 8th. Oh, you're right. The absolute value of
Yeah.
A would be way more accurate.
Yeah, because
It's
a negative number
negative.
doesn't equal its absolute value.
Right. It's like they were fresh after writing the chapter where they're making the variable positive in every case.
Yeah. Yeah, so that's one of the pitfalls of kind of like sometimes using negative A where A is positive and sometimes just saying A is
Right.
less than 0.
They were it, that was exactly the confusion.
Yeah. Let's see. So yeah, so the 8-bit binary representation of 2 to the 8th minus absolute value of A. Yeah.
So,
And then this is the procedure for adding. So like to add two integers in the range negative 128 through 127, whose sum is also in the range negative 128 through 127, you blank, 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 and blank.
let's see.
I guess you would first write the binary representations of each number, the
Right.
8-bit binary representations of each number. Yeah, and then you add them. I guess add the numbers in binary.
I suppose you could drop the overflow bit.
Yeah. Yeah, so drop the overflow one or the one in the 2 to the 8th position,
Yeah.
the 2 to the 8th place, if there is one.
Right. And then find the two's complement if it's negative.
Yeah. Yeah, find the 2's complement and then add a negative sign.
Mm-hmm.
Yeah. Yeah, and I guess the book they don't list that step. They just say convert to decimal form, but yeah, you're right that
Oh.
should be yeah, they should have had that in the answer too.
To represent a non-negative integer in hexadecimal notation means to write it as a sum of products of the form. So it's
It's gonna be
d.
like digit times power of 16, so like d times 16 to the n,
Um,
where n is a non-negative integer, and d equals any of those 16 digits 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, a b c d e f.
oh,
Yeah, or I guess you can say like d is a digit from 0 through f, I guess.
Let's see. Right, so sum of products of the form d times 16n, where d is what? Yeah, right.
Yeah,
It's
d is,
a digit or an integer between 0 and f.
yeah, I guess maybe you could call them digits, I guess, because they're kind of like treating them as, I guess they do represent integers. But yeah, I guess you could maybe say an integer for, between 0 and f, or a digit, like, cause indicating that those are just like the symbols, 0 through f.
N would be the digit place. D would be an integer between 0 and f then.
Yeah. Yeah. Oh, yeah. Yeah. The n does correspond to like what place you're in. Yeah. Yeah. The 16 to the 0 power, the 16 to the 1 power, etc.
The sum of
Yeah.
products. Okay, yeah.
Yeah. And it looks like the way the book does it is they say like just d equals 0, 1, 2, etc. 9, a, b, c, d, e, f. So like it just equals one of those.
It equals 1 of what?
One of the 0, 1, 2, etc. all the way through f.
Oh, it doesn't use like an ellipse or anything like that?
Oh, they do use an ellipse. They say like d equals 0, 1, 2, dot, 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 9, a,
Oh,
b, c, d, e, f, which is another way of saying the same thing.
see. Convert a non-negative integer from hex to binary notation. Non-negative integer from hex to binary notation. You just
So I guess you write the 4-bit binary representation of each digit.
juxtapose them.
Yeah.
Um,
Yeah, the 4-bit binary representation of each digit.
each, right.
Yeah. And then it's also important that like it'd be like binary, like a 4-bit binary.
You can't. It won't. It won't ever require more than 4 bits, but I suppose specifying 4 bits would eliminate any zeros beyond the fourth bit.
Yeah, because if you like represented some of them with like different numbers of bits, then like that whole thing with shifting everything to the left a certain amount of places wouldn't have, like, it wouldn't work out.
True. There.
Yeah, good. Yeah, so we did finish that chapter.
Nice.
Yeah, yeah, that was nice to do a bit of math. Or I guess it was more than a bit, like 8 bits of math.
Whoa, that was a good one.
Thanks. Yeah, yeah, that was fun. I see the next chapter is about like predicate logic. So it's like kind of adding more structure to logic.
Virtual logic.
Yeah, like now I'll be able to talk about like every cat is a mammal. Like, because previously we didn't have any symbol for every and like some cat is domesticated. Like previously we didn't
Oh,
have any way of saying like there exists some cat that is domesticated. And it also gonna have like a way of talking about like properties like um this um or like Athena is a cat, like that's like applying the property of being a cat to Athena, and then like this predicate logic is going to have properties as well.
okay.
And also you'll be able to talk about like individual objects or individual entities. Um, yeah, so definitely something to look forward to.
Good. Sounds like a fun area of logic and math. That
Yeah,
binary stuff was probably the hardest stuff that we've run into so far.
yeah, definitely. Yeah, I found it definitely the hardest. Yeah, yeah, I think this chapter is, or this, at least this section here is going to be a lot more straightforward compared to that.
Nice.
Yeah, kind of returning to logic. Although the binary, I guess, had some applications of logic connected to it.
True. It did. It did. Hmm.
Yeah.